Both experimental and theoretical nuclear physicists undertake research in the NC State Physics Department. Because of the nature of the field, these studies take place at a variety of laboratories, including Oak Ridge National Laboratory, Triangle University's Nuclear Laboratory, in the department's own Riddick Hall, and at the university's nuclear reactor Pulsar, where low-energy neutrons and high-energy beta rays emerge in the reactor's shielding bath. Here, blue Cherenkov radiation occurs when relativistic particles supersede the speed of light in the water of the bath. It's here that Professor Albert Young conducts much of his research.
It's not the relativistic charged particles, but the neutrons that we cool to about 1/10 billionth of their original energy to make ultra-cold neutrons for our experiments.
If you want to make something cold, of course, you got to have cold stuff to make it cold. And so that means that many of our experiments take place in a cryogenic environment, where you have a system hanging off of a cryostat and some dewar at liquid helium temperature, 4 degrees, and then down below that, you've got some high-power refrigerator that can bring the entire system down to 100 millikelvin or 200 millikelvin in that range, where the sample is extremely cold and the ultra-cold neutrons can cool down as well. We have a nuclear reactor where we can make an ultra-cold neutron source. We have a nuclear laboratory where we can construct large-scale cryogenic apparatus and do associated tests of the infrastructure for delivering polarized material into cryostats. We've got that present locally. It's really an incredible resource. The heart of our activity is for many of us, very fundamental questions. Where does the matter come from? Why was there more matter than antimatter? This is a big question we don't even, you'd think at this point we'd have some kind of answer for, but we don't. We don't know why there's more matter than antimatter. A big chunk of our effort is just a quest to find an answer to that core problem. What caused that baryon-antibaryon asymmetry? And we can probe that by looking for example, a static electric dipole moment of the neutron. You shouldn't have a static electric dipole moment. But if one is present, it heralds new physics. It heralds physics right now. If we saw one, it would mean there's new physics. And that physics can help us explain where the baryon-antibaryon asymmetry comes from. But it's enormously challenging actually making this measurement, which is one of the reasons why we have to turn to things like ultra-cold neutrons to do the measurement, because these measurements require preparing a sample of particles with a known spin and then storing them for a very long time inside of a storage cell and measuring the way that they respond to applied magnetic and electric fields. In the course of doing our fundamental research, we often find ourselves also touching on more practical questions. Could you create a very compact gamma ray source that you could use for experiments for isotope detection, perhaps even for food irradiation if you could make it very, very intense? Could you make a source of gamma rays which was very, very localized using a laser? So you shine a laser on a material and it emits gamma rays after it hits the material. Now, for that to happen, the energy of the laser in the single little light packets that it's made of, the photons, has to be converted to a much higher energy single photon phenomenon. And there are not many ways that you can do that aren't very costly and very inefficient. So we were hoping to amplify this process using nanoparticles. And it gives us a chance to combine expertise in the department. We have nanoparticle experts who can make exactly the nanoparticles we want. We have laser experts that can allow us to put together a very intense pulse laser that we can direct onto the system. And we have nuclear physicists that know how to interpret the gamma radiation and make sure that we've properly illuminated backgrounds. It's a nice team.
With facilities ranging from nuclear reactors to sophisticated cryostats. With faculty solving theoretical and experimental problems. And with studies, both basic and applied, the NC State Physics Department works at the forefront of nuclear physics research.